Problem 1. For the series magnetic circuit, find the value of I required to develop a magnetic flux of phi equals 4 into 10 to the power minus 4 Webers, and then determine mu and mu r for the material under these conditions. So the actual structure is like this, where the number of turns is mentioned, n equals to 400, I is something which we have to determine, phi, that is magnetic flux, is given, A, area of cross section, is also mentioned, length of the core is 0.16 meter, and the material used to make this core is cast steel. The equivalent magnetic circuit for this structure will look like this, where the magnetomotive force determined by using the formula F equals Ni will be over here. Phi will look like this, and reluctance will be represented in the form of a resistor. Remember, this is designed using an analogy of electric circuits, where F represents the voltage source, phi will be the analogy for current, and reluctance is the analogy for resistance. Now, when you solve problems based on magnetic circuits, always write down a table like this. Then you can fill in the given details in the question paper, and looking at the table, you can understand what are the variables which you need to determine. For example, by looking at this table, we can say that we have to determine B, H, and HL. So, at first, we can determine the flux density B using the formula phi by A, which will be equal to 0.2 Tesla. Now, we can determine H. In order to determine H, we will need the BH curve, which we have seen in the previous slides. We know that the material used is cast steel. Then, using the BH curve for cast steel, for a value of 0.2 Tesla, we can find the corresponding value of H, which will be approximately 170 ampere turn per meter. Now, applying Ampere's circuital law, we can say that Ni will be equal to HL. Over here, we know N, we know H from the BH curve, we know L from the given information in the question. Thus, we can easily determine I, which will be equal to 68 milliampere. Now, we have to determine mu and mu r. From the BH curve, we know the value of H and we know the value of B from the given information in the question. We know that B equals to mu H. So, substituting the values of B and H, we can easily determine mu. Mu R is basically the relative permeability of the material. Mu R equals mu by mu naught. We have determined mu over here, and we know that mu naught equals 4 pi into 10 to the power minus 7. Hence, we can easily determine the relative permeability, which is 935.83. That is, this material is 935.83 times more permeable than air. Example 2. For the electromagnet in the given figure 12.14, it has two sections. Determine the current I required to establish the indicated flux in the core. So, if we consider the electromagnet over here, the core is built from two different types of material. One is sheet steel and the other one is cast iron. The length of the sheet steel is from E to F, F to A, and A to B. and the length of the cast iron is E to D, D to C and C to B. All the lengths are mentioned over here. The area of cross section throughout the electromagnet is 1 inch square and phi equals 3.5 into 10 to the power minus 4 Weber. Observe carefully. The magnetic field lines or flux passing through both the material, that is flux, is same 3.5 into 10 to the power minus 4 Webers. The number of flux or field lines will not change. So at first we have to make this table. That is, we need to write down all the variables, that is phi, A, B, H, L and HL, and then we need to fill in all the necessary information from the question. After that, the first step would be to convert all these lengths into SI units. By looking at the table, we can tell that phi, A and L are the informations which are given in the question, and we need to determine B, H and HL. So, B will be the same for both the sections because both phi and area of cross section A are same for both materials. Thus, B will be equal to phi by A equals 0.542 Tesla. The next variable which we need to determine is H. The value of H will be different for the different materials used. Using the BH car, we can determine the value of H for sheet steel corresponding to value of B of 0.542 Tesla, which will be equal to 70 ampere turn per meter. And the value of H when the value of B is 0.542 Tesla for cast iron is 1600 ampere turn per meter. Now we can determine HL for each section. For HEFAB and LEFAB, the value will be 21.34 ampere turns, and for the other section, the value will be 203.2 ampere turns. Now that we have all the required values of each variable, we can determine the equivalent magnetic circuit. Using Ampere's circuital law, we know that NI will be equal to HEFAB times LEFAB plus HBCDE times LBCDE. We know the number of turns N from the given question. Thus, we can easily determine I, which will be equal to 4.49 ampere. That is, you will need a current of 4.49 ampere to set up phi of 3.5 into 10 to the power minus 4 Webers. The electric circuit analogy for the electromagnet will look like this. The analogy for F in the magnetic circuit will be E in the electric circuit, and the reluctance of each material could be replaced by the resistance R. Determine the secondary current I2 for the transformer in figure 12.16 if the resultant clockwise flux in the core is 1.5 into 10 to the power minus 5 Webers. So, the product of N1 and I1 can be represented in the equivalent magnetic circuit as F1, and the product of N2 and I2 can be represented by F2 in the equivalent magnetic circuit. The resultant flux will be in the clockwise direction. Hence, phi is in this direction. Since only one type of material is used, sheet steel, thus reluctance will be represented by one element. Now, in the equivalent electric circuit, note that the resulting flux of each is opposite, just as the two sources of voltage are opposing in the electric circuit analogy. As always, we have to make the data table at first and fill in all the necessary information. At first, we have to determine B, which will be equals to 5 by A and equal to 0.10 Tesla. Then, using the BH curve, we have to determine H, which will be equal to 20 ampere turn per meter for B equals 0.10 Tesla. Then, using Ampere circuital law, we have to determine the value of I2. N1 I1 minus N2 I2 will be equal to H times L. Now, some of you might ask that why are we subtracting N2 I2 from N1 I1? This is because in the question it is mentioned that the resultant flux is in the clockwise direction. In that case, the value of N1 I1 will be greater than the value of N2 I2. From there, we can determine I2, which is equal to 3.89 ampere.